Okay, this is the continuation of the 5.2 notes from in class on last week. Just going through some of the examples that we had to skip over. This is the rule that says if we can get the same base on each side, one base on each side that matches of an equal sign, then the exponents are also then going to have to be equal. 27 and 9 do not have the same base, but they both have base 3. 3 cubed is 27, and 3 squared is 9. By exponent laws, a power means we multiply, so we would distribute this. So that would be 3x minus 3. Distribute this. This would be 3 to the 4x minus 6. Now we have same base on each side, so we set the powers equal. I would add 6 over, subtract 3x over, so we get that x equals positive 3. So that was, remember, a property that we learned in class. The next thing we did with exponentials is that we learned how to graph them. We said that this is pretty basic. You can just do a table of values. And as long as they haven't changed your exponent, like added anything or multiplied or subtracted anything up here, then your table is pretty safe if you just do negative 2 to 2. So this would be negative 3 to the negative 2 power, negative 3 to the negative 1 power, negative 3 to the 0 power, negative 3 to the first power, and negative 3 to the second power. Essentially, because this negative is not in parentheses, it stays out front. We move negative exponents and bases to the bottom. So this is negative 1/9. This would be negative 1 over 3 to the first, which is negative 1/3. And remember, you can use your calculator for all this. This is just negative 1 because of the negative out front. This would be negative 3 and negative 9. So if we plot these points, negative 2, negative 1/9, negative 1, negative 1/3, 0, negative 1, 1, negative 3, and 2, negative 9, we see that this looks sort of like our exponential function, but it's upside down or reflected. And it still has that horizontal asymptote at y equals 0. Okay, the next one I'm going to look at actually does have a change to its exponent. I want to show you what that does. If you have like an x plus 2, we talked about in class that you don't want to start your table with negative 2 to 2. Your table needs, just to remind you, what x plus 2 equals 0 is. This would be the middle number in your table. That just helps you make sure you get your table set up correctly. This one is just a negative x, so it's still going to be okay to plug in negative 2 to 2, but they're going to all flip signs. So this would be 3 to the negative negative 2. That would just be 3 squared, which is 9. 3 to the negative negative 1. That would be 3 to the first. 3 to the negative 0, that's still just 0, so that would be 1. 3 to the negative 1 would be 1 over 3. And 3 to the negative 2 would be 1 over 3 squared, which is 1/9. So notice it flipped the whole direction or reflected us across the y-axis, if you remember from transformations of functions. Which this guy, sorry, should have been positive. I don't know why I put a sign on 0. He doesn't really have a sign. And then this would be 1 1/3 and 2 1/9. So notice if your exponent is negative, you get a decay model instead of a growth model. What I want to show you is that actually is the same thing as 1/3 to the x power, because we learned in our definition of an exponential function that if your base was less than 1 but bigger than 0, you actually get a decay function. So we'll show you that this guy actually is the same graph we just did. So 1/3 to the negative 2 power means that the whole fraction flips, which would just make that 9. 1/3 to the negative 1 power, whole fraction flips. 1/3 to the 0 power, anything to the 0 power is 1. 1/3 to the first power is 1/3, and 1/3 to the second power is 1/9. So notice this is same as e. So I'm not going to regraph it, but it's the same function. So kind of to show you why that happened is because if you have this negative exponent right here, you can actually think about breaking it up as to -1 and then to the x power, because that is still saying -1x if you multiply the powers back together, and that is how you get the 1/3 is being the same as this. So just kind of something interesting that happens with these exponentials. Okay, the final thing in this video for 5.2 is that we're going to start talking about some word problem applications. Yay! Okay, yeah, very excited. I like word problems. So there's two big things that we want to talk about in terms of exponential functions: radioactive decay and compound interest, things that might actually show up in someone's life. So certain physical quantities decrease exponentially in such cases if a is the base of the exponential function and a is between 0 and 1. One of the most common examples of exponential decrease is the decay of a radioactive substance or an isotope. The half-life of an isotope is the time it takes for 1/2 of the original amount in a given sample to decay. The half-life is the principal characteristic used to distinguish one's radioactive substance from another. The reason this is important is if you're trying to get a test done that needs an isotope or something for checking for cancer or something like that, if they don't order enough, they can't do the test. So they have to actually think, if it's not coming from somewhere close by, how much extra do I need to order so that when it arrives at my location, I still have enough to perform the test. So it's kind of, it's important to know that these things are decaying so that you get the right amount. So compound interest is another application that we're going to look at. It's a way to talk about growth. If a sum of money P, which is how much you've deposited or invested or borrowed, that's called the principal, is invested at a simple interest rate R, then the interest at the end of one interest period is P times R. So, for example, if I have $1,000 and an interest rate at 9%, that would be 0.09. At the end of one full year, I would have $90 in interest. If that interest is then reinvested with the principal at the end of the interest period, then your new principal would be P plus PR, or, because that's your original amount plus your interest, P times 1 plus R. Now, we would keep going with this, and over time we find out that if you increase the number of periods of time that you're going to do it, you actually get compound interest, which is that interest is accumulating on top of the original principal and extra interest. So our formula, so I'm going to kind of skip through their description, is right here. This is one you need to know how to use. You don't need to memorize it. P is the principal, R is the rate is the decimal, N is the number of times they compound. So like if they're doing it quarterly, you have to know that that means 4 times a year. Semi-annually would be 2 times a year. Annual would obviously be 1. Monthly is 12. Some of them are very, obvious. Weekly is 52. Bi-weekly is 26. So just realize that you have to know that that's your N. It's how many times are they compounding it. And then the little exponent has N and T up here. You can't see it, but that's an N times a T. The T stands for the time in years, and the A is how much money you would have at the end of the investment. Okay, so let's go through some of these word problems. Drug dosage. A drug is eliminated from the body through urine. Suppose that for an initial dose of 10 milligrams, we know that the amount in your body after T hours later is given by the formula 10 times 0.8 to the T. Estimate the amount of drug in the body 8 hours after the initial dose. So that means they're just telling us to plug that in. So 8 is going in for time. So 10 times 0.8 to the 8th. We need our calculator for that. So 0.8 to, not times. 0.8 to the 8th power, times that by 10. Looks like that is 1.7 milligrams. Then it says, what percentage of drug is still in the body? Still in the body is eliminated each hour. Well, we'd have to get a couple hours estimates to know that. So why don't we do the hour right after this one? So 0.8 to the 9th. So 0.8 to the 9th power times 10. That'd be 1.3 milligrams. And the way to figure out the percentage is you have to do what's called a percent change. That's when you take the new amount, subtract the old amount, and then divide it by where you started from, which is the old amount, and then turn that into a percent. So this is something that they expect you kind of to know, but a lot of people don't know this formula. So we would do 1.3 is the new, because that's the later hour than the original, minus 1.7 divided by 1.7, because that was from the previous hour. So 1.3 minus 1.7 divided by 1.7, and you get negative 0.24. So that's approximately a 24% decrease in your drug amount in your body every hour. Okay, so let's look at my next one. It says if 10 grams of salt is added to a quantity of water, then the amount that is undissolved after t minutes is given by this formula here. So a lot of these, they provide the formula for you. Sketch a graph that shows the value Q of t at any time from t equals 0 to t equals 10. So we would need to kind of get a trend here. So Q of t equals 10 times 4/5 to the t power. I would just make a little t chart. If we plug in 0, that would be to the 0 power, so that would be 1 for that, but times 10. So that would be our initial starting point. So let's get our calculator. So let's count by 2s. So 4 divided by 5 to the 2nd power, and then times that by the 10 out front. That's 6.4. So that's when I plugged in 2. I'm going to plug in 4, 6, 8, and 10. So we know that 0.8 is 4 divided by 5. So 0.8 to the 4th power times 10 is 4.1. And then 4 divided by 5, I knew that was 0.8, but 0.8 to the 6th power times 10 is 2.6. And 0.8 to the 8th power times 10, we already know this one, we just did it, was 1.7. And 0.8 to the 10th power times 10 is 1.1. So if we wanted to graph this, we would only need the first quadrant because it's all positive. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's my first point. 1, 2, 2 was at 6.4. 4 was at 4.1. That guy went away. And then 6 is at 2.6. And 8 is at 1.7. And 10 is at 1.1. So notice it's a very slow decline, and I cannot draw with this tablet pen, but it is declining and decaying. Okay. The next one is a money problem. So if $1,000 is invested at a rate of 7%, so that would be 0.07, compounded monthly. So this is my rate, this is my compounding, and this is my principal. We want to find out how much money would we have 6 months, 1 year, 5 years, and 20 years. 6 months has to be converted into a year because this is a formula that uses years, so that would be half a year. So remember for your formula, it's A equals P parentheses 1 plus R over N to the NT. So this one is going to be for the half year. So we're just going to do these one at a time. So this would be 1,000 times 1 plus 0.07 divided by 12 to the 12 times a half. I always find out this power first before typing it in my calculator. That's 6. So then when we type it in with the parentheses, just like you see. Oh, sorry about that. So this would be 1,000 times parentheses 1 plus 0.07 divided by 12, close parentheses, to the power of 6. That's approximately 1,035.51. So 1,035.51. And you would need to put a dollar sign on that since that is money. Okay, let's do another one. So now we're going to do the 1 year mark. So these are our values we're plugging in. So 1,000 times 1 plus 0.07 over 12. 12 times 1, which means we're just plugging in an exponent of 12 this time. So 1,000 times 1 plus 0.07 divided by 12, close parentheses, to the 12th power. That gives us 1,072.29. So notice extra 6 months, we have about an extra $35 or more. Then 5 years, which this is trying to show you the power of compound interest. The longer it sits, the more money you have. 12 times 5 is 60, so our exponent is 60 to this time. So 1,000 times, open the parentheses, 1 plus 0.07 divided by 12, close the parentheses, raise the power to the 60th. That's 1,417.63. Notice we're starting to see more of an increase. And then after 20 years, which is quite a bit of time, our formula stays exactly the same, except now it's 12 times 20 on the outside for years, which is a 240 exponent. So 1,000 times parentheses, 1 plus 0.07 divided by 12, close parentheses, raised to the 240th power. That's 4,038.74. Now that's not a lot of money, but you only invested $1,000 at the beginning. So the more you invest, obviously you'd see bigger returns on this. The last one on this page or this section is if a savings fund pays an interest rate of 6% compounded semi-annually, which means n equals 2, r is 0.06, how much money should you invest now so that you will amount to $5,000? That means we want $5,000. Side note, if solving for P, always round up. That is because you don't want to short your goal. Okay, so we're saying A equals P parentheses 1 plus R over N to the NT, and this is for 1 year, so T is 1. I know that A is 5,000. I don't know P. 1 plus 0.06 over semi-annually, which would be 2. 2 times 1. Because we're solving for P, we're going to divide that big parentheses over, and it's essentially just squared because 2 times 1 is 2. So on our calculator, we would type in 5,000 divided by parentheses 1. If you don't put the parentheses, it won't divide, right? 1 plus 0.06 divided by 2, close parentheses, squared, and then we would hit enter, and that's 4,712.97. Even though that 9 bumps you up already, we would round up anyways. So 471298. I think I just said that wrong. Yeah, 1298. This is supposed to be a 2. Okay, and that is the end of this edited section.